This is Shivani, and I'm working as an associate data scientist at AiSPRY. And the previous project which I worked upon was related to IVF. Okay, and that project was all related to AI powered follicle detection and measurement. So these follicles and this IVF, this process might be maybe it is new for few of the people. So let me just illustrate and show you few things. Like in general, IVF process is meant for those couples who are not able to conceive naturally. So what happens in the IVF process is that the sperm from the men and egg from the women are taken and it is fertilized artificially in the labs in order to give them a give them a chance to produce children. And in that process, a lot of different stages takes place, and in every stage there can be an involvement of AI. So right now this project deals with the follicle basically. So looking at the picture, we can see that there is some yellow kind of structure and there is some pink kind of structure over that yellow color, and post that we are able to see some a big change, uh, a big change over there. So this is known as a primary follicle. Okay, and follicle is basically where the egg is stored. Okay, so this is a primordial follicle, and then it becomes a primary follicle. Post that, when like for every each and every stage, there comes a change in the size of follicle. There would be some changes happening at each stage, making it into a developing stage. And then at last, like we could see in the illustration itself, first it was a primordial follicle, then it became a primary follicle, and then secondary follicle, post that antral follicle, and then pre-ovulatory follicle. So what happens is the egg gets released from the follicle. So basically, this is a mature follicle. Generally, the mature follicle is measured in the Okay, so generally, the follicle, when it reaches the size of 18 to 22 that particular follicle is considered to be a follicle which could give us a mature egg. And so generally this process is all done traditionally manually. Okay, so in that process, in that process embryologists are required. So what happens in that process is that people, uh, the patients basically, the patients who come for this kind of regular continuous treatment, what happens that few of the embryologists which they come for checking of these follicles, they might they might try to count it in a different manner. The follicle, the mature follicle, they try to count it in different manner. Maybe that count is different from the other embryologist who comes in a next to visit and tries to look for the same patient. So this is where the inconsistency comes into picture. Inter observer variability comes into picture. Apart from that, the other loophole that a traditional way of counting the mature follicle comes is when there is a lot of time consumption. In traditional way, each and every follicle is measured from each and every angle using ultrasound process. using ultrasound process. That is how it is done. So coming to the problem statement, it the traditional way is time consuming. Manual follicle assessment takes 3.5 minutes per scan versus 6 minutes 6 seconds automated. Like if an embryologist is assigned for counting the mature follicle, counting overall the follicles. If the follicles are less, then it will take less time. But if in case the follicles are too much, then counting each of the follicle accurately and looking at that the count is not missed is a biggest task. Inconsistency, higher inter observer variability between the clinicians. Impact on the outcomes. Pregnancy rates range 28.2% to 40% based on the antral follicle count. Delayed decisions. And because of all these above mentioned problems, there would be a delayed decision which could cause variability and delayed treatment decisions, and eventually it may lead to lower IVF success rates as well. Because if the follicle is not measured properly, then there might be a chance that we may miss a better good quality of egg, and therefore there would be a chance of lower IVF success rates. Right. For that, the solution which AI can provide is an AI powered automated follicle detection and measurement system that standardizes monitoring, saves the time, improves the clinical outcome, which can reduce the time from 3.5 minutes to less than 30 seconds, which is a very vast, vast difference when AI is applied. It is very, when it comes to less number of patients or less number of follicle count detection, it might look very less. But when it comes to a real case scenario, it is really an impactful change. Consistency. Less than 5% coefficient of variation. Objectives or accuracy variability. To maximize the accuracy, accurate follicle detection and measurement. Reduce the variability. That means to minimize the time consumption and observer variability. Adoption target. L- Less than 5% coefficient of variation eh, and more than 9% clinician adoption within 6 months. Technical targets, more than 95% MAP at the rate zero point 0.5, and more than 92% dice coefficient, and less than 2 seconds of inference. That is what it is expected. And expected business impact is 85% reduction in examination time. That is 3.5 minutes to less than 30 seconds, which is a very big impact that AI can bring. That is how it helps in in this IVFs, where time is very crucial. And then decrease in the cost per second. Decrease in the cost per second, less than or equals to 60% decrease in the cost per scan, less than or equal to 200% ROI within 12 months of deployment, 3x more patients per clinic per day. This is how it impacts the business as well. Right. So coming to the data that we have, uh, this is the data I could show you. Um, so this is a follicle and this is the shape of follicle basically. So we had one kind of class, that is follicle. Only one kind of class that we had was follicle, because we had all the ultrasound images, and post that we took those images and we tried to run a model, and try to give a AI solution which could detect the follicle, the mature follicle, and which could also measure the follicle. Right. So import CSV, that is import OpenCV. Import OpenCV. That is here the part is where the all libraries have been installed, and then comes the code where we have uh, where we have imported all the images that we have, and then we have loaded the image files which contained all the images of follicles of which were in the ultrasound, which were the gray scale images basically. And we checked it using this code. We checked it whether the images got successfully successfully imported or not. And then the list was created in order to store the pixels. So basically what had happened is we had converted the pixels into uh, in order to measure it. We have converted pixels into for each of the measure to measure the mature follicle. Process for each image. A loop was created: image path, folder path, image name, and image CV2, CV2 dot read image path. Image path is what we have given previously. So yeah, this is the image path which we have. This is the image path variable that we have given. And apart from that, converted the image to grayscale for easier thresholding. Already it is, but we have done it in order to make it in a better manner. Then coming to applying of a binary threshold to detect the bright white scale lines in order to make it more easier, the detection part to make it more easier, we have done this. 230 threshold value, very bright. 255 max value for detected pixels. CV2 dot threshold gray 230 comma 255. CV2 dot threshold binary. Morphological cleanup. So some kind of pre-processing was also done using RoboFlow itself before we come up with this kind of code, the model you can say. So the pre-processing steps and all that augmentation was also done in the RoboFlow itself. So kernel np dot ones 3 comma 3 np dot uint 8. Okay. This was to create a small kernel for noise removal. If at all any noise were there present in the image itself, in the data itself, it was used to remove that noise. Apply morphological opening to remove the small noise. Detect the contrast. Find the contrast from the binary image, and for only the outer contrast. So this kind of steps were taken up in order to ensure that the data which we have used should and must be in such a way that it gives better accuracy, line length, and then loop through all the detected contrasts, get the boundary rectangle around the counter. Right. So this was all done. Then aspect ratio was also calculated. W by float h. width by height. That is what it was done. If aspect ratio is greater than 5, so yeah, greater than 5, and 2 is less than W, and then it is W is less than 500 and H is less than 10, then the line will append W, right? Calculating the pixel per mm. So this was where the append, sorry, this was where the pixel, basically the pixel got converted into mm. This pixel was converted into in order to make sure that we are able to you know give some better result. Obviously, when the images are given, it would be in a pixel format. It won't be in a format, and the follicles are continuously moving. Because the follicles are continuously moving, so the conversion of pixels per was something which was needed. So basically, this images and all that stuff uh, made the images were taken from the videos itself and then were converted into frames. And post that, those frames or images, you can say, that was pre-processed in the RoboFlow, and then it was taken for measurement and detection. Final collaboration result. Check if the at least one valid measurement was found, and if found, if found, it could then get saved into a file. This is how we have done it, and I hope this project explanation gave an immense knowledge, and how an AI can help even in the field of medical, even in the field of IVF. So that's all from my side. Thank you and have a nice day.